Today we're going to talk about force, and we're going to introduce the concept of force and the things we're going to be doing today. We're going to start off with things that are really obvious and so easy that it will at first seem kind of confusing. We're going to go through a series of activities where it's going to be real easy at first, then it's going to be pretty easy, and then it will be a little bit challenging, the last one. But it's all going to represent the same basic idea. But there's a few things we need to know before we start doing the activities. And one is, what is this thing that we call force? What is force? What is it? Well, here's what in physics what we mean by a force. Here's my coffee mug. No more coffee in it. And let's zoom out. Okay. Let's see if we can get that in focus. Okay, and so I'm going to apply a force to this coffee mug. Are you ready? All right, so I'm going to apply a force to it. So here we go. Here we go. Wow. Okay. Or, now, so this is what we call I'm pulling on it, right? I'm pulling on the coffee mug, and I'm making the coffee mug move. Okay? I can put a string on it. Do the same thing. Here's a string. String the coffee mug. I can pull on it. So that's a pulling force. Okay? Or I can do this. Whoa. Okay, I told you this was going to be easy. Force. 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 Ah. Okay. So, a force is a push or a pull, and it can change the way an object is moving. So that's pretty basic, right? A force is a push or a pull. It's a push or pull that can move an object around, or change the motion of an object, however you want to put that. Let me zoom in so people can read it. All right. I'm going to be zooming in and out a lot with this. Okay. Now, what do you notice about force, though? What kind of quantity is a force? In order to describe a force, what do I need to know about the force? I mean, what's different about this force? Okay, I'll zoom out again. It's going to be annoying. Ooh, look at this force. Okay, I'm pushing on it. I'm pushing on it. I'm pushing on it all the way to the edge of the table. All right, what about this force? What's different about those two forces? The direction. So what kind of quantity do we call it if it has a direction? Yeah. Force is a vector quantity. I can push on it this direction, this direction, this direction. So force is a vector quantity. So we can add that on here. And maybe I'll just write bigger on the paper so you can read it without me zooming in and out. Force is a vector. Okay? So that is, it has a magnitude and a direction. And we're gonna identify its magnitude and direction. We're going to put it in polar coordinates. Now, how do we measure the magnitude of a force? Well, let's see. What if you want to know how much force of gravity is on you? What do you do to measure your force of gravity? Well, I get up in the morning and I'm hoping that I've lost some weight, so I stand on a
mountain.
A mountain. I would like to throw you off a mountain. No, this is, you stand on a bathroom scale. Okay? And actually, I guess if you were at the very, very top of a mountain, you would weigh ever so slightly less than you do at sea level. Not enough less that you would even notice it. We'll talk about that when we talk about Newton's law of gravity. But what's different ways of measuring a force? Well, we have pounds, right? Pounds. You can measure a force using pounds. We don't use pounds to measure force, though, in this class. We are going to use this unit of measure. The Newton. The Newton. No, we're not going to use the apple. We're going to use the Newton. Now, it so happens that this toy foam rubber apple, when you hold it up, the gravity pulls down on it with 1 Newton of force. Or if you hold it in your hand like this, you'll feel 1 Newton of force pushing down on your hand. It weighs 1 Newton. Weight is a kind of force. We'll talk about that more later. So a Newton is not very much. Newton is a very small amount of force. It's not nearly as big as a pound. A pound is about 4.5 times bigger than a Newton. Okay? It's named after Sir Isaac Newton. Okay, to honor him and the amazing discoveries he made. Isaac Newton was one of the greatest minds in the history of the human race. He was kind of a jerk, Newton was. Not somebody I would want to party with. But he was nevertheless an amazing human being who did amazing things that we remember to this day because he changed the world we live in. So, but anyway, so what I'd like to do, I'm going to throw this around. Here, who could catch? Who's paying attention? Okay, ready? You did? Oh my gosh.
What's that?
Okay. Huh?
That's a me?
Yeah.
Oh. Well, I tried catching it.
Yeah, I'm sorry. Just pass it. I'd like everybody to hold it, get a sense of what a Newton of force is. Now, so if I were to draw a force, I would draw it as a vector. Like if this is my coffee mug right here, looking down on my coffee mug, I might push it this way. So it would have a certain number of newtons. That would be its magnitude. And of course, we could measure its angle. And so it would be in polar coordinates. Or I could take my coffee mug and I could pull on it. So same thing. Push and a pull does the same thing. So they have different magnitudes and directions and so on. Those are forces. And they can pull things, move them around. But do they always move things around? Well,
What does that do?
yeah, be careful with that. That's my pride and joy, that Newton apple. Okay, how I'm going to take my coffee mug and I'm going to push on it like this. Okay, you guys pay attention. Stephen. All right. So look at this. I'm going to do this, and this one says, Okay, I'm having a battle here. A force battle. I'm going to crush this. All right. Notice that the forces can cancel each other out, right? If I add this vector plus this vector, if I add two vectors that are in opposite direction, they tend to cancel each other out. Yes? Does that make sense? So there isn't, if I push on the coffee mug like this from both sides, the force, there are not zero forces on the coffee mug. If I let go, it's going to go like that, or if I do this, it's going to get pushed that way. But the forces can add up to zero. They can cancel each other out. And when an object is not changing the way it's moving, or if an object is at rest and is staying at rest, when an object has no acceleration, we say that that object is in equilibrium. Equilibrium. If an object is in equilibrium, let me go ahead and zoom in. What does that mean? For our purposes, like the equilibrium has different meanings in different, like in chemistry, they have equilibrium and so on. But why don't you give that to me, because it's distracting people. Thank you. It means the object is not changing its motion. Another way of saying is the object is not accelerating. Okay? So that's what we mean by equilibrium. An object is at rest, and it's staying at rest. Or if it's in motion, it's staying in motion. Like if you're drinking, if I am drinking this, coffee, I got some coffee and I put it on my table on a train. Let's say I'm having some coffee on a train, and the train is just moving at constant velocity down the track. The coffee mug is in equilibrium, even though it's moving compared to somebody outside the train, but in its own reference frame, it's at rest. Another way of saying it is that an object is in equilibrium if it is at rest in its own reference frame. Okay. So what we're going to do is we're going to do a series of activities for objects that are in equilibrium, and we're going to learn something about the forces that are acting on that object. Now, the object doesn't have to be a coffee mug. It can be something very light and small, which I have here somewhere. Before we do the activities, I need to show you this. These are spring scales. This is how we measure how many newtons a force has. Now, I can take this coffee mug and I can pull on it, and I can measure the pulling force using a scale. So here it is, and I can put a spring scale on it. And the string is too long. Kind of a klutz when it comes to real objects. So I can pull on this, and I can measure how much I'm pulling on it with the spring scale. Not very much. Okay. So now I can't push with it though. Spring scales can only measure pulls. I mean, what happens if I try to push on this string? Okay, I'm going to push. It just doesn't work. Another way of saying is that you can't push with a rope. Where I'm from, that was an expression. Can't push with a rope, but you can pull. All right. So when you're pulling on something, you are measuring of the pulling force. You can do that with this spring scale. And here's the spring scale, and I'll show you how to use these things here in a second, how to measure the force. Come on, you can do it. There we go. Now notice that there are two scales on this particular spring scale. There's newtons and there's dynes. I have another one where there's newtons and grams. Never mind the grams. We're going to use newtons. Now the first, is everybody watching? Because people got the wrong answer last period because they weren't paying attention. I know this goes on and on, but listen. You need to zero your spring scale. If you lay your spring scale down and just kind of get it ready to go, and it looks like that, you're going to be off by 1 newton. Ignore the dynes. We do not dyne in this class. Okay? We use newtons to measure force. And so you want to adjust this and make sure that the very center of this tab is at 0. And that looks pretty good right there. And then you can measure the force to the nearest tenth of a newton. Now I'm going to pull on this and hold it, and I want you to tell me how many newtons of force I'm pulling on this spring scale. What is that? 6.5? I'd say a little tiny bit more. What? 6.6? I'd say 6.6 because the center of the tab is a little bit beyond. Now, if you said 6.5 or 6.7, that's pretty good. If you said 6.1, that would be wrong. 6.9 is wrong. And 6.6 was pretty close. The 6.5 is pretty close, and that's what we want. We want to be, that last digit needs to be within 1 of what you're measuring. See? Now there. What is this one? 8 point? What? No, 9 point? Yeah, 9.1. Okay. So if you said 9.0, I'm not going to argue with you. If you said 9.2, I go, it's a little bit much, but okay. If you say 9.4, I'm going to, no, that's wrong. You see what I mean about measuring? Getting that last digit is a kind of a guess, but there is information there. Now, if I did this, and I said, oh, okay, that's 10.67943962 newtons. That's horse manure. Okay, those last few digits. Okay, you can only measure the nearest tenth of a newton using the spring scale. So we can measure the magnitude, and then we can use protractors and so on to measure direction of forces. So here's what we're going to do. Now, we're going to take, I'm going to give you some strings with loops in them. And we're going to do activity 1. Okay, now, we're going to take a loop of string. Oh, sorry. We're going to take a loop of string and we're going to pull on it. Yep. Here's the hook, and then here's the spring scale. Here's your handle. You're going to pull on it this way. And we're going to call this F1. And then you're going to pull on it in the opposite direction with another spring scale. We're going to call this F2. Now what I'm going to do is I'm going to give you several F1s. And I want you to measure F2. Now this is going to seem so easy that at first it's going to seem kind of a big stupid waste of time. But it's not. It's one of the most profound ideas in all of physics. These are forces. They're vectors. So in order to describe a vector, I need to describe a magnitude and a direction. So let's define direction. Let's say this is the positive x direction. This is the y direction. Now we're not really using the y direction yet, but we will. I'm going to go 5.0 newtons, 10.0 newtons, 15.0 newtons. And what angle is this? 0 degrees, 0 degrees, 0 degrees. And what I'm going to ask you to do is give me the magnitude and direction, magnitude and direction, magnitude and direction of F2. I want you to really measure it. Now you might think you know what the answer should be, and that's okay. You've got a hypothesis based on previous experience. That's fine, but I want you to measure it. Now to get accurate results, make sure that your spring scales, both of them, you're going to use two of them, start at 0. One group got these really wacky answers, and it's because they didn't zero their spring scales. And I want you to give me this in polar coordinates. Okay, and then when you do it, I'm going to turn this into more work than it should be. For each one of these, I want you to go what is F1 plus F2? Now what do you have to do to add vectors together? Okay, you have to change them into rectangular coordinates. So I want you to put these into rectangular coordinates before you add them together. And it's really easy to do that on this one. Okay, so I want you to do this in two places. I want you to do it on your whiteboards, and I want you to do it in your notebooks. Okay, I'm going to pause the video now. So I want you, and then we'll hand out the materials and do the experiment. Okay, so pause the video now.